Minimizing charisma, maximizing intelligence, shooting someone in the crotch with a cannonball, thrust, propulsion, it's science-y.
Why you always gotta be blowing my spot up like that? There are my runes. There they are. I'm not mad. Science needs art and art needs science. They both need each other to function properly.
There are ways to figure out what the paper is really saying.
And then I'm ready to get on Twitter and yell at people about doing their own research on...
Oh, hold on there, sports fan.
Karl Hill, everybody! He's the next generation of science communicator. I'm gonna be too old at a certain point to do those terrible things to my body, and it'll be up to you.
He's got like a lion's mane. This guy's amazing. Kyle Hill.
I'm Boo Rambo.
The universe is indifferent to you. Whether or not you have amazing hair, the universe doesn't care.
How are trees pushing past this pressure limit? Ah! Behold, my balls. Now we're getting somewhere, but I still don't think it's worthy of G.R.R. Martin's suspender.
I'm totally right? Close up photos of my frickin' hair? Is that what you all want? No, you don't, weirdos.
Kyle Hill. Is your last name actually Hemsworth? What's going on?
Our resident Thor lookalike?
I prefer Black Friday Chris Hemsworth.
Oh, thank you.
Hey, you know, if you need a haircut... No, of course not! We're not gonna send sharks with frickin' laser beams on their heads to an asteroid. We're gonna nuke. You don't need Bruce Willis at all. Wrenched. Oh! Headshot! Oh! Kevin, turn on the monitor. Kevin, this transition better work. The blast doors can't... Kevin, turn it on. Kevin. Thank you. Kevin, call his agent and have them call my agent.
Kyle Hill, happy birthday. Feliz Navidad.
I'm just a biologist. I don't know how this works. This is how you do science. Can I just grab it? Oh. Laws, corollaries. Bye-bye.
I know that global catastrophe isn't the most fun thing to think about all day unless you're me, so...
Are we gonna do some science, bro?
Lasers don't have that much momentum.
That's not how clockwise works.
Don't worry, you can do this even if you are not an AI.
Completes the boundary layer around a person through a dynamic. And I guess it matters what kind of dragon we're talking. To realize here is that the bigger the thing does.
If this kite is completely inaccurate, I'm gonna kill this guy and tell him to his face. You're wrong about physics. Not enough lift force. Oh.
Nuclear metal donut thing with magnetically confined star-like plasma. The radiation flux in here alone is enough to cause instant death.
That's really funny. I like that idea.
Hey, look at me. I'm a streamer. I have a bedroom. We know anything with a decapitation hazard deserves to, yeah.
Ooh. Oh, that's good. That's fine.
Put it on PBS. I dare you. I don't know. What are you going to do? Well, I mean, you can see the kind of power we're dealing here with at the facility. I mean, look at this tokamak. It's toka amazing. Shut up. It was fun. I would like a bicycle that goes so fast I release the chains of gravity on this planet and soar up. I guess that is a plan. I don't know. What are you going to do with all your free energy? You can't fit that many burgers in there. All right. Sorry, I got something to do. Okay, love you. Bye. What? Oh, wrong number. Sorry. Chat. Welcome to the facility. Welcome to the core of my tokamak fusion reactor. This is a good place to start out today's Office Hours podcast because today we are talking about a new breakthrough in fusion energy, as we will get into and explore and explain everything underneath the stars and beyond, as we like to do here in Office Hours. We will explain what this means for today's fusion industry, what this means for fusion power going forward. Is this a breakthrough? Is it more of a milestone, like rules are to pirates? We'll talk about everything here at the facility, but first, I have to get out of this neutron flux. I am cooking my genetics. Chat, welcome. Welcome to Office Hours, a live component of the facility where good old Professor Kyle opens up his glass doors and allows all of you members of the public, my security team, Crafty, Jabo, all members of the facility here inside of my heavily shielded walls for the next hour or so as we explore and explain everything in the week of science that made me go, hey, hell, wow. We'll be also taking your comments and questions as we do so. If you want to continue on this conversation after we're live, of course, you can join the facility. Going to patreon.com/Kyle Hill. Join the facility today for private Discord, videos early, all that good stuff. You can go to the gaming channel. Tomorrow, we will be streaming Next Gen Witcher 3 update. I'm very excited about that. And, of course, can't promise to get to all of them, but you can try Super Chat here on YouTube. Know that even if I don't get to it, it is still going towards the facility, everything we do here in an educational manner, and fixing that light. Like Troy Thompson with the 20, first time catching live in a while, just wanted to say thank you for all you do. You inspired me to be an engineer. Even when it gets tough, these vids help keep me going. Troy, I am so gosh darn proud of you. To be a part of your educational journey is why I started doing all of this in the first place. I appreciate it. What's wrong with the music? I know the music's on. Which music? I can hear it now. I have it turned. It's loud? Oh, it does look a little loud. Sorry. How's that? Anyway, we can't hear you now. It's great. Can't stop the music. Smidge loud. All right, we turned it. Turn it down. Is it just me or is Kyle very red? Says Susie Cyanide. What? Chat, we have to get to this. Susie. How about that? Anyway, I was told by one of my cousins who likes to watch Office Hours that last time we talked about fusion energy, I took way too long to get into it. So,
let's get right into it, talking about today's quote-unquote fusion breakthrough, what it means. Chef Julie with the $9.99. Sorry to do this at the top of the stream, but my line cook, Kyle, locked himself in dry storage and got into the peanut butter again. What a fool. CMAP with the Australian $10, which means, you know what this means, chat, it's time to work on my perfecting my Australian accent. G'day, Karl. A workmate handed me a bottle with about 250 milliliters of 20 ppm U-238 solution, mass spectrometer calibration standard, and asked if I'd drink it for $1 million dose. Good deal or nah? No. The if you're gonna be irradiated, the worst place to be irradiated is inside your body. That is the least amount of shielding, the closest to your organs for the longest amount of time. When we're talking about the danger of radiation, we're talking about TDS, time distance shielding. And being inside your body is the worst place to be because it's the closest, the longest, with the least amount of shielding. It's a perfect impression shot. What does this fusion breakthrough mean? There was a quantum physicist reacting to your videos and disagreed with a few of the things that you said, says Game Over Jesse. Quantum physicist. I saw the nuclear physicist, and she said I was spot on. Not too bad on the accent. Still needs work, says Dada. Damn it. Hey, Enterprise Warp Core. Exactly. No square. So, today's fusion breakthrough comes from this place, the Lawrence Livermore National Laboratory and the National Ignition Facility. Yo, Kyle, love the show. Finally able to catch you live, but can't stick around. Take my simpage. Thank you, Dante King. Being a true king. Go off. So this is a National Ignition Facility. You may recognize it, some of you nerds, as the engine of the Starship Enterprise in the new Star Trek Into D and associated movies. J.J. Abrams actually was able to go into this laboratory. What you can't see at the bottom here, this is all this is all surrounded by concrete, because concrete is less likely to be activated by radiation, of which there's a lot in here. And so what J.J. Abrams actually did so he could shoot up, there's two floors. You stand here, there's like a floor below this, see that? And it's separated by thick concrete. J.J. Abrams paid millions of dollars to cut a hole out of this floor just so he could point his cameras up and look at it, which I think is crazy, but cool. Anyway, it's cool because this facility is the largest laser facility in the world. And when I'm talking about large, I'm talking about large, chat. The width of 3 football fields for all you Americans. For all of you Europeans and everyone else in the world, I don't know how wide a football field is. Anyway. So this breakthrough comes at the National Ignition Facility. Underneath that comparison there, you see all these tubies. And all those tubies, 192 of them, funnel lasers. And those lasers, a massive amount of electricity, like terawatts worth of electricity, gets turned into laser light. That laser light gets reflected, amplified, redirected, split, and it all comes down into a spherical chamber, the engine of the Enterprise. And it all is focused on one thing. Now, we can cover the fusion basics in a second, but because my cousin who watches the show says I didn't get to the point quickly enough last time, let's get quickly to the point. So, once all those 192 lasers... Oh, how do I know all this, chat? Because I was there, Gandalf! I was there. 3,000 years ago. National Ignition Facility, me in a Fallout suit. Anyway, I was there. So, you focus all these 192 lasers down on this tiny, tiny little point. Something that is like a centimeter long. And this centimeter... So, here's a fun thing, chat. Most of you, I guess...
ladies' fingers might be different in proportion, but dudes' fingers are about exactly an inch at this phalange here. And an inch is 2.54 centimeters. So this Hallram, as it's called, this target, is about a centimeter long. So that's about half of this. So it's very small. And not only is it very small, it's very technical. It's very, very cool. This Hallram holds a tiny pellet of deuterium and tritium. Now, you nerds also may know what those things are from Spider-Man, but deuterium and tritium are just fancy names for heavy hydrogen. Heavy hydrogen is just hydrogen with extra neutrons. Hydrogen is just a proton with an electron. Deuterium, 2, H2, not, they call it 2H. It's not 2, it's diatomic, but it's H2 is a hydrogen. It's just proton, electron, neutron. Tritium is an extra neutron. Okay? So, this is very good as fusion fuel in this little pellet inside of this casing, which again is called a Hallram, because deuterium and tritium is it's aside from hydrogen, it's the lightest element in the universe, isotope in the universe, with the least amount of nuclear repulsion. So you want to force these things together with temperature and pressure via lasers, but you want enough mass to get some energy out of them in this fusion reaction according to E equals mc squared. Music still a bit loud? There's no music. Jacob. Get it together, Jacob. Inside of this Hallram, the lasers do not hit it directly. Now, this is the little sphere of deuterium and tritium, the fuel. Why don't you hit the fuel directly? Well, given that this thing is only about a centimeter, and you're talking about 3 football fields worth of lasers trying to hit it, any slight deviation could create instability. You hit it just a tiny bit off center or whatever, something could blow out the side, etc., etc. So to create a spherical inertial confinement, as this is called, using inertia to confine and compress this fuel, to get a spherical, more orderly compression with the inertia of this Hallram, the lasers actually come inside and immediately obliterate the Hallram, the casing. The obliteration of this casing forces a shock wave in, and that shock wave compresses the fusion fuel down to star-like temperatures and pressures. And that's when fusion can happen. More technically, you can see the lasers coming in, hitting the Hallram, and on the far right, you see the implosion creates, the X-rays create an implosion, which compresses the heat with heat and pressure, like hundreds of millions of degrees, which creates the fusion burn. So it's like an implosion. It's literally an implosion. As German, your pronunciation of the word Hallram is distressing. Okay, Kurt, tell me what it is. Now, these are the basics of what we are trying to do. This is one way to create a fusion reaction, ignition. The power of the sun in the palm of your hand. There's a tokamak, like you saw at the beginning of the stream, but this is that. This is the what you'll see is inertial confinement fusion. Lasers obliterating a casing, using that uniform obliteration to compress fusion fuel down very quickly. So on to today's breakthrough. At the National Ignition Facility, at the National Ignition Facility, this is the chain of energy. So they're putting like 400 megajoules
of energy into those 192 lasers. As these lasers are reflected, split, redirected, oriented to hit the fuel, it is an extremely inefficient process. So you can see, starting with, say, 400 megajoules, don't need a comparison for that, it's a lot. 400 megajoules, by the time it gets to the fusion fuel on the far right there, 1 megajoule left is actually hitting the fusion pellet in the form of those X-rays that comes from the casing that was obliterated. So a loss of 400 times. That's incredibly inefficient. That's not even 1% efficient. Still, it's a lot of energy hitting a tiny little pellet. And if you hit that pellet in the right way, it causes the heavy hydrogen, remember, deuterium and tritium, to undergo that fusion reaction, overcome the nuclear forces, force them together, and this reaction releases energy according to E equals mc squared, even though this is a tiny, tiny little pellet. Because E equals mc squared, energy equals mass times the speed of light squared, the speed of light, 3 times 10 to the 8th meters per second. That's a big number. Then multiply that number by itself, and then multiply that number by your mass. Even if your mass is very small, multiplying it by many millions and millions of times can still give you a lot of energy. So today's breakthrough is going from that purple to that yellow part of what you're seeing right now. How is energy collected after the reaction? It says, I'm Arion. I will discuss that shortly. So what has been announced today is that from about a megajoule, I think they used about 2, they got ignition, and then they got about 2 or 3 megajoules out. That means that they got out more energy than they put in to the ignition reaction. Okay? This has never been done before. And I wouldn't call this a breakthrough. I would call this a milestone. You can think of 3 milestones that we actually want to hit. The first is being able to create ignition, the conditions under which fusion can occur. And that is no simple feat. We've been trying to do... Oh, who am I, the Try Guys? We've been trying to do this for decades. So to create the conditions of a star on Earth, it's incredible. Milestone number 1. Milestone number 2 is today. To get as much, if not more, energy out of the ignition reaction. They put in 1.3, they get out 2. We did it. That is the essential proof of concept of fusion energy. Okay? So let's hang on that for just a moment. That is the essential proof of concept. That we created a system that can release the immense amount of energy inside of atoms. And I want you to really think about the enormity of this energy. Fusion reactions release 1,000,000 times more energy than the equivalent mass of a fossil fuel. So if you had a lump of coal, a lump of fusion fuel reacting would equal 1,000,000 of these. Put it another way. Maddie La with some good combinations. Put it another way. All of the deuterium that I could get out of a bottle of water, if I fused it in a good fusion reaction, good fusion reactor, it could power your house for a year. That's it. 1,000,000 times is a lot, chat. This is why fusion is the end goal. Fusion would eliminate energy costs. Pretty much. It's unlimited. It's free. Basically. Because a bottle of water power your home for a year. We'll get to the caveats of that in just a second. So we've hit milestone number 2. But Karl, what about milestone number 3? Thank you for your handsome question. Milestone number 3 is the problem. Chat. Look at the left-hand side of this image and the right-hand side. 400 megajoules in to the lasers, and the predicted yield that we can get to today at the very best of conditions is 20 to 40. See a discrepancy there? So I'll remind you that today we announced that we got 2 on the far end there. We created more energy than came into the pellet, but we were 20 to 40 times. Oh, actually, sorry. Hundreds of times less than what we need to equal the energy we're putting into the system. This is why this is milestone number 3. If we put more energy into unlocking the atom than we get back, we're not fully unlocking it, are we? Right? So, milestone number 2, we got more energy from the pellet than we put into the pellet. But we were still 10 times away what the theoretical ignition yield, far right, 20 to 40, might be at the NIF. And that's still 10 to 20 times less than the energy we're putting into the lasers. Okay? So we're still talking 1 to 2 orders of magnitude that we need to increase efficiency. Look, we're only putting 1 megajoule onto the pellet, and we're putting in 400. We need hundreds of times more efficient processes. And we're looking into this. The lasers, the setup of the entire system. Which leads us to the power. How we're actually... So, milestone number 3. Well, this is actually... So, okay. Let's step back for a second. Recruiter for Team Basilisk with the $50 from the Basilisk Recruiter. Thank you. Hey, Science Thor, been a while since I've been able to catch a live stream. Just wanted to send some holiday cheer to keep up the good work. You present science in a fun and easy to digest format. All hail the Basilisk Recruiter. Thank you so much. I will ensure you will not be tortured forever. So, as I just developed this milestone system off the top of my head. First, create ignition. Been there, done that. Second milestone, today's breakthrough. Create more energy than you put into the fuel. We have 2 more milestones to go, chat. Milestone 3, we just said. Get more energy out of the entire system than you put in. We're 10 to hundreds of times away from that. Milestone 4, and this is the hardest part, make all that make power. Power is very simple. As we have talked about, chat, nuclear power is just using spicy rocks to make steam, basically. Why are you yelling? Says Chef. Calm down. Why are you yelling? Astro Marine, thank you for the 10. I like your anime avatar. All of the power that we use is basically just to make steam. And this is what we want to do with a fusion reactor. As you can see, the pump, whether it's a laser, some sort of magnetic field, which is the Z-pinch there, the pump creates the ignition. We get heat from the ignition, hot and fresh out the kitchen. Some of that goes and turns turbines, turn water into steam, turn turbines with the steam, get electricity. Some of it goes back into the system. Making a better laser and converting the heat to energy are engineering problems, not physics problems. They can be directly solved with time and money, says Matterbeam in the chat. Exactly. So the first 3 milestones, the first 2 are more physics, the last 2 are more engineering, and so this is the big problem. This is why, even though today's milestone is a tremendous one, the engineering problem is immense. As someone in the chat asked before, how do you turn all this into electricity? Like I said, you capture the heat, but how do you capture the heat? This is non-trivial, chat. The designs for something that captures the heat efficiently are immense. Designs that will take decades to make and implement, massive billion-dollar investments. Look at the size of that truck. That's a semi-truck on the far right there. Late to this party, hope you're well. Welcome, Murph. Iskander says, use a very good coat. You're almost exactly right. So the last milestone, chat, is to figure out what's called a blanket. And the blanket, not a coat, you were so close. And a blanket is the thing that surrounds the nuclear reactor and gets heated up. And then what you do is you siphon the heat from that blanket and you heat up water with it. Now, how do you do that practically, Kyle? Well, when a fusion reaction happens inside of the Starship Enterprise engine core, as we've been talking about at the NIF, when that fusion reaction happens, neutrons fly out. Now, if you capture those neutrons with something, if you make it go through some shielding or some stuff, it will heat up that stuff. Then it's just a matter of, say, putting that stuff through a heat engine-like process. So getting that stuff in contact with water, heating up the water. This is what a blanket is. So imagine, the inside of this giant sphere. Pellet inside, gets hit with lasers, fusion reaction happens, neutrons come out, hit the walls are surrounded by a blanket which gets hot. That hot blanket turns water into steam. Now, the coolest, well, I'm not an expert, obviously, but one way to make all of this work, there's problems. Obviously, there's problems. But one very interesting way I've seen to make this all work is called the LIFE engine, which stands for Laser Initiated Fusion Fission Engine, or LIFE reactor, also developed at the Lawrence Livermore National Laboratory. You're looking at it right here. There's a problem with tritium, chat. It's very rare. Deuterium you can find in seawater. It's essentially limitless. Tritium is much harder to come by. So how do you solve this problem? Let's make the coat. Let's make the... you ruined me, chat. Let's make the blanket, the thing that gets heated up. Let's make that out of something that makes tritium when it gets hit by those neutrons we're trying to capture. Ooh, scientists are smart. Turns out, lithium, not the Nirvana song, but lithium is very abundant in Earth's crust. And lithium, when it reacts with a neutron, can produce tritium. Sniper with the 5, it was awesome to meet you two at MTG30. Thanks for stopping by the stream. So lithium can make tritium. So what we do is we put a blanket of lithium around our nuclear fusion reactor. We let it get heated up by the neutrons until it's molten metal. And then we constantly circulate that molten metal around, putting some of it in contact with water, siphoning off the tritium gas. And now we have a hot blanket that stays hot, that makes our water hot, that is also producing tritium that we need for fuel. And then we can get even crazier with this, chat. Remember, we're far out in the future now, so let's get futuristic. What else can we do, chat? Well, this life reactor says, well, why don't we also put fission fuel around the blanket or with the blanket? Spent nuclear fuel, depleted uranium, weapons-grade plutonium. Let's put that with the blanket, because when it gets hit by neutrons, it will also fission, just like in a fission reactor. But this part is not critical, so it's not going to explode. We just keep that hot too with the neutrons we're already making. So now with this ultimate nuclear fusion reactor, we have fuel going in, lasers smashing this pellet down to create fusion. Fusion releases neutrons. We capture the neutrons in the hot lithium blanket. The hot lithium blanket gets siphoned off, gets constantly recirculating, put it in touch with water. Water creates steam. We create power, but we're also getting even more heat out of the system because we're capturing more neutrons and creating more neutrons with spent nuclear fuel, everything else that we could use from all of our fission reactors. 99% of it burns up in this reaction, and almost all of it is used. We get an energy gain even after all those lasers of 4 to 10 times, and energy has become limitless. Unlimited power. So I know, chat. I know that was a little technical. There. But that's the be-all. That's one of the be-all, end-all designs. So, to recap, chat, where are we today? We are past milestone 1. That is achieving ignition, hot and fresh out the kitchen. Actually, I shouldn't say that anymore because that guy's a monster. We've achieved ignition. Milestone 2 we hit today, which was getting more energy out of the fuel than we hit the fuel with. Milestone 3 is getting more energy out of the fuel than we put into the system. Step 4, creating a sufficiently efficient nuclear fusion reactor that can capture the heat with some sort of blanket, whether it be lithium and all this other depleted uranium, all that kind of stuff, whatever it is, but a blanket system that can capture neutrons and transfer their heat into steam and water. To date, no fusion facility is anywhere near a blanket or a blanket design. We are only trying to do ignition, net energy production. So we're stuck at milestone 2. How long will it take to reach 3 and 4? I don't know. When I was there in 2018 at the NIF, I think they had achieved ignition. It's been 4 years since then. It's hard to say. Given that we are between milestone 2 and 3, remember, getting more energy out of this whole football field size system, given that we're at least tens, if not hundreds of times further away from our estimate than we want to be, it could be a very long time. As I said in the poll in the chat, before 2100, I don't know. I would say that by the end of the century, having something commercial, which is, sufficiently efficient, full-scale system, like this dang thing, I think that's right. I don't know. It's hard. Predicting the future is always impossible, but that's right near pushing it. Next couple decades. Before 2050, I don't know. Probably after. If you had to ask a non-expert like me, and we have experts in the chat who've been nuclear engineers who've been fact checking me. So today, chat, that's where we're at. We're at milestone 2 out of 4. Exciting, but we're not quite yet at having fusion power your homes. Kyle, I swear we had an announcement from the National Ignition Facility just some time ago. Am I right? Yes, with a 10. Thank you. They got a lot of energy out of a recent, and we just did a video on that. This was more important than that. I don't know if it was energy. Oh, I think they achieved unity, right? Getting the same amount of energy that they put into the pellet. This is they got more. So that's a significant milestone. Hey Kyle, says Crispy, with the 10, one of the most prolific members of the facility. Patreon.com/Kyle. Hey Kyle, one of the Kevins got into the Xandarian wine, and tried to use Lola's back as a slide. He was yeeted into the eternal exhaust vent. Deck 41 needs to be rescued. You said external exhaust vent. I said eternal exhaust vent. I like that better. Chat. Tomorrow, on the gaming channel, one of my favorite games of all time is coming out with a next-gen update, The Witcher 3 Wild Hunt. We'll be playing through it on the gaming channel. We'll be checking out all the new updates, which I'm excited about. We'll be running it on ultra settings, hopefully. But we'll see if we can science a hard fantasy game. I think we can. Wouldn't the lithium blanket be a bottleneck, says Stunt94? No, lithium is abundant in Earth's atmosphere. Crust. In Earth's crust. It's a metal. And we can mine that. I mean, again, if we have enough lithium for lithium-ion batteries, it shouldn't be an issue. First time I caught you live. Love your stuff for years. Shout out to my Madagascar science class as archery enthusiast. Welcome. That's super cool. I'm glad I got to know about the state of fusion energy today. This is a cool live, says Fausto Gomez. Well, Science Thor is the White Wolf, Geralt of Rivia. Wasn't fusion ruled out by all the YouTube nerds? Why the change of heart? I don't know specifically who you're talking about. But I don't know. Fusion is definitely not ruled out. It's like we said, it's an engineering problem that will take a long time, probably. It's not a physics problem. We've proven that we can achieve ignition. So if you're ruling it out practically, if you're saying it's going to be decades, then yeah, maybe. But I don't think it's ruled out entirely. The sun creates fusion through gravity, says Trevari Goldstein. You want to know an interesting fact about the sun, Trevari? Of course you do. It's my show. The sun is not hot enough and intense enough in pressure to create fusion on its own. Cold fusion was ruled out. Yes, definitely. The sun, through its heat and pressure, cannot mathematically create fusion reactions on its own. Thankfully, or else everyone would be dead and no one would ever have lived in the first place. But thankfully, quantum tunneling happens enough in the interior of the sun that the fusion can still happen and overcome energy barriers that they couldn't otherwise overcome. Quantum tunneling is the reason you're alive. And everything else. The sun is a miasma of incandescent plasma. I wouldn't say it's a miasma, even though that's probably a lyric to like a They Might Be Giants song. The sun, another interesting fact about the sun and other stars are more or less perfectly spherical. Because they are so big, with so much mass, their gravity, which acts in all directions pointing towards the center of mass, that acts to spherify the star almost perfectly. Can we capture energy in another way, says Drycon? The heart of all, whether it's fission or fusion, it's just capturing the byproducts of the reaction, which have energy and turning that energy into heat. There's a lot of proposed ways to capture that heat, but just having something in the way, making it hot, and then boiling water with that hotness, that's the basic concept. What is quantum tunneling, Kyle? Says Arade Sobajo. Quantum tunneling is when a particle crosses a barrier, crosses an energy barrier that it wouldn't be able to do classically. So think of a ball and a hill. And the ball, you want to push the ball up and over the hill to the other side. Now, if you calculate exactly how much energy you need to do that, and the ball, you don't push the ball hard enough, it's just going to go whoop, whoop. Quantum tunneling, since particles are not really objects, they're like probability waves, like a wave of light, but probability. I know, it's weird. If the barrier is sufficiently small and the probability wave is sufficiently large, that wave, there's some probability when these two interact, there's some probability that that particle will be measured on the other side of the barrier. And that's what quantum tunneling is. And it happens in the sun, and it's why you live. So the blanket pretty much needs to be a giant AC system with refrigerant to move the heat, says Amicable Duck with the 5. No. It's not a... there would be no way to cool down that whole system. It's more like heat exchanging an immense amount of heat out of the system. So it's not refrigerant. It is... It's not even really cooling. Like we're saying, I'm talking about, like, if this blanket was lithium, it would be at 1,000 degrees Kelvin, or 1,000 Kelvin. It'd be molten. Then, what a heat exchanger is you have two opposite running systems. Say you have, it's going to be more complicated than this, but let's just say it's a tube of hot lithium. We take that hot lithium, we pipe it in the opposite direction next to a tube of cold water. When they pass each other, or as they're next to each other and flowing inside, enough heat is transferred from the lithium to the water to heat up the water into steam on one side and to keep the lithium from going too hot. It's just look up heat engine or countercurrent heat exchange. Same thing. Whew. Sean, if you're watching, did I explain that all in a timely fashion? Say hello to your kids for me. Kyle, what do you think the practicality is for using AI, much in the same way we use AI to solve engineering problems we face with Fusion? Kiss Metatron with the 5. AI can... What's intriguing about AI is that it can find solutions that you didn't even know existed. Because it's not human, it could look at a data set or a problem in a way that is non-human and find patterns, find recognition that you couldn't even conceive of and deliver you something interesting. So, for example, a very powerful AI, and I'm going to forget all the names, but a very powerful AI was given thousands of molecules to look at as antibiotics. Antibiotics are very important these days with all the resistance evolving everywhere. Now, going through and evaluating each molecule for potential antibiotic properties would take thousands of humans many, many years. This AI was able to almost, I think it was like within hours, find an antibiotic that no one had ever even conceived of that had widespread applicability. Like that. Basically, relatively speaking, like this. And we're like... And do you know what the when I say it's non-human, do you know what's interesting, chat? The AI doesn't even know what it is. You can't ask the AI, why is this a good antibiotic? It doesn't know. It's just looking at patterns and data. It can't tell you. Isn't that interesting? So those are the areas where I see AI doing something really amazing. Large data sets that humans will never physically have the time to evaluate, and finding patterns that human minds couldn't even conceive of. Is the antibiotic in use now, says Jackie Johnson? I believe it is. No, I know it was discovered. It was discovered recently. I don't know if it's in trials or not now. Let me see. This was 2 years ago. Yeah, we did a... Did we do a show on this? What the heck what's the name of it? The name of it, if you want to look it up more. Yeah, so it looked through 100 million chemical compounds in days. Just days. Like, before the weekend. Say the name of it. Oh, it's some... Oh, I remember it's named after the AI in 2001. What is it? Halcyon. I knew that. Is it in use yet? Preliminary studies suggest that halcyon kills bacteria by disrupting their ability to maintain an electrochemical gradient across their cell membranes. So it is being studied right now, chat. And an AI found this when no one else could. And there's the link to it! Is this the same like morphine? We know it works, but not how? No. So the scary thing, my friends don't, well, some of my friends don't like when I point this out, but like, we don't know how a lot of medicine works. Like, we know that it works and we have ideas, but we're not actually sure. But it's so useful, we still use it. Like, we're not totally sure how anesthesia works. But we use it anyway because it's so incredibly useful. You don't know the exact mechanisms. That's different. I'm talking about an AI not even knowing what it's looking for. It's just, you're saying, you're giving it all these variables and you're just saying, find this combination of variables in the data somewhere. And it will find it, but it doesn't know why, and it doesn't know how. Would it be possible to use an AI to calculate the basic organic materials and compounds needed to start terraforming other planets? It's Tyler with the Canadian 5. No idea. But, because I'm not in the field, but again, training AI on a large data set will reveal patterns that might be interesting in a timeline that would be impossible for humans to do. That's what's interesting. Kyle, what would you do with $44 billion? Says Matthew Rogetzer. I wouldn't spend it just to be booed on stage for 10 minutes. Loser. Michael Griffin with the timely donation. When will you do Musk Watch 2 Electric Boogaloo? Says Michael with the $1.99. Never. Never. I have lost all respect. Well, what would I do with $44 billion? $44 billion is more money than God. It's just it's an obscene amount of money. You can do whatever you want. Scrub Express says, I've just been banned from Twitter. Oh well. I haven't used Twitter in like a month or so. What do you think will be bigger for mankind? Fusion power or room temperature superconductors, and why? Says Arlen Kundert with the 5. Fusion power. Superconductors are already here. What we're trying to do now is find ones that you don't need to cool down to liquid nitrogen temperatures all the time. And superconductors are important for maglev trains, MRI machines, particle accelerators, all this cool stuff. But fusion power would impact anything with electricity. Anything. Which our entire civilization is built upon access to electricity. And if access to electricity becomes trivial, i.e., there's enough to go around, there's no blackouts, there's no shortages, and it costs you nothing, or next to nothing, pennies on the dollar, that would completely change all of society, right? I'm not even talking about any of the cool stuff, like being able to get from here to Jupiter in a couple of months or whatever, with a fusion rocket, but having electricity be free would change everything. I'm not wearing headphones, but I'm finally pumping the music you're listening to through the facility speaker, so now I can hear what you're listening to. Tell me if it's too much. Is it still too high? Looks like it's a little too high, huh? How's that? $44 billion is enough to spend $77,000 every hour for 65 years. That's what I'm talking about. Love you, says etc. Love you. Music was fine. All right. Bump it back up there. I'm testing it out, chat. I don't want to... It'd be... If I had headphones on, this wouldn't be an issue. But I don't want to wear them. Music is amazing. Where can we find it? It says 100th fail. Search for White Bat Audio on YouTube. They have free, royalty-free music that you can use, and so I use them. And they are great. Chat. I know we haven't been publishing very much lately. We did the Callisto Protocol episode. We did the sponsored live stream. We haven't been posting very lately, and that is because we have been stuck trying to figure out a dang fundraiser for the dogs of Chernobyl. The video is done. It's great. The puppies are adorable. They're currently freezing their cute little butts off in Ukraine. I want to raise tens of thousands of dollars for them. The problem is that it has been a bitch and a half, see what I did there, to get this particular charity integrated with YouTube's backend so that when I publish the video, it says fundraiser and you can just click the button. Okay? I've been trying to do that since October. We are at the final step of the approval process, I think. So hopefully before the end of the year. And then we'll get back on track. Back on track, meaning through what videos do well on the channel and through my polling of all of you. When I poll and tens of thousands of you vote, you say, do more Half-Life histories, if not do them almost exclusively. I'm not going to do them exclusively, even though I probably should. But we will return to form next year and have at least once a month, if not two. And that should grow the channel, grow the audience, satisfy all of you. And it'll be good all around. When does your TV show come out, says Joey Zoom. We just signed a contract with a production company that I can't tell you about, and we are in development. Haven't sold anything yet. What I can tell you is I'm actively developing a TV show at the moment. The freedom you felt when you first started those first 3 videos were and still are amazing. Kyle, whatever content you feel like making, make it. Yeah, we'll do more Half-Life histories, and if I, quote-unquote, run out of topics, which I won't for a while, nuclear isn't the only thing I'm interested in. We could expand the format to talk about other things as well. Well, history of... It couldn't be... I don't know. I like the format we have. I like the more measured, somber, documentary style approach, like true crime approach. It doesn't have to just be about nuclear stuff, but Kyle's irresistible progression towards dominating all forms of science media is continuing on schedule. Yep. Yeah, next year might release some sci-fi movie commentaries that you can listen along with me and some guests with. We're continuing to grow the gaming channel, which tomorrow we will start our journey through Next Gen Witcher 3, which I'm very excited about. I want to turn Expedition Chernobyl, which is the collection of all of our videos that we did last year. I want to turn that into a quote-unquote movie, a longer form, hour-plus long video that you can watch all in one go, have everything revamped, change the VO, all that stuff. Might visit Fukushima next year. I have lines on going to a nuclear waste site, going on a nuclear-powered aircraft carrier. A lot of cool things next year, chat. Hopefully. I saw a nuclear physicist YouTuber reacting to your Chernobyl video. She was quite impressed. Yeah, I saw that video, and I could tell from her thumbnail she was expecting to be disappointed, because she's and that's fine. She's mostly reacting to other people, you know, talking about nuclear waste and nuclear power and saying, like, you know, this is a misconception, this, that, and the other thing. What she wasn't expecting is that I do my research, chat. And then the whole video, she's like, oh, yeah, no, that's right. Oh, this is great. So that made me feel good, because I'm not an expert. And so to have experts say that I'm doing a good job, or that I'm at least correct, is very validating. And I know a lot of you in chat are either work in the industry or you're physicists, so that makes me feel quite good. Benjamin Wheeler with the 5. Thanks for all the great content, Kyle. Really appreciate all your work and effort putting out fantastic videos. Will you do any live tours in the future? And if so, can you come to New Zealand? It's the same Blake. I would love to come to New Zealand. I would love to. You're not an expert, but you do play one on TV. I was saying in Discord yesterday, it's weird that I can text Adam Savage. Crazy. No, I mentioned the TV show. I'm actively developing a show, and we're working with a production company, but we haven't sold anything, and I'm not going to tell you anything, but I'm just saying, many irons in the fire, chat. Garnicus 2. I've been hooked on the alternate history hub. Would it be possible to see a science-based version of that? Probably not, because I'm not a history expert or buff. What I like about Half-Life Histories is that it takes me a long time to do, because you weave the educational aspect into it. So, you know, I could just say, you know, criticality accident happened with the demon core, this guy died. But what is important to me is to show the science of what happened, to explain how these things actually work physically, so that we can demystify what we're talking about. And that's exactly why I went to Chernobyl. My point, and you know, if you watch those 3 videos, Chernobyl doesn't look like you think it may have looked, right? It's not a glowing wasteland. It's not, you know, 4,000 people work there every day. There's puppies running around. There's a cafeteria with good food, you know? And so knowledge is power in this respect. By exploring and explaining these things in a dispassionate way, then we can see past bias, right? To most people on the street, you say Chernobyl, they think it must have been the worst thing to ever happen. It's not. Drew B, I want a hammock in your hair, Kyle. Chat, it's been a good stream. Tomorrow, we will be doing the next gen Witcher 3 stream. I'm super excited for it. I don't know what we're gonna do, whether it's start a new game, continue where I left off, or start a new DLC game where we're already at like level 35 and play like Blood and Wine and something. But I want to go through everything that's new. I want to get the Witcher armor from the TV show. I want to do all that stuff, and we're gonna talk about, see how much science we can get out of a fantasy game like that. Again, one of my favorite games of all time. It's the only place on YouTube where you can see a scientist game and science your favorite games. Kyle, did you get a picture of the food at Chernobyl? It would be interesting to see that, says Chef Julie. The food at the Chernobyl nuclear power plant is good. It's very traditionally Ukrainian and Russian. I didn't get any pictures because there's a lot of tourists there taking pictures, and that seemed gaudy to me. I don't know what the right word is. But we were there with the explicit permission of the government and with the power plant. We were there with scientists and experts. I didn't want to look like a noob. You know what I mean? You know, I think it would be good to go on Moist Critical's official podcast. Kaya loves nuclear energy like you. Tag him. Seems like a nice guy. Actually, I like his breakdowns and stuff like that. I think he's very funny and very smart. So I'd do it. Great stream shot. Kyle enjoyed it. Remember, chat, at the very end, what did we talk about today? We are at milestone 2 of fusion energy. We have accomplished ignition. We are now getting more energy out of fusion fuel than we put in. Next steps, we got to get more energy out than we put into the entire system, and then we got to make this system make electricity. That's what we learned here today. Chat, if you want to continue on this conversation after we are live, just a second, kind of optimal wideness. If you want to continue on this conversation after we're live, go to patreon.com/Kyle Hill. Join the facility today. I know many of you in the chat are already professors, research assistants, interns at the facility. You help me grow out this place. You directly support us. I appreciate it. You can go to the gaming channel, sub there. You'll see the Witcher stream there tomorrow. I know many of you, you're asking about the time. I don't know yet. Depends on when I get up and feel like it. And find my Witcher pendant. So subscribe there and you'll get the notification right away. Thank you so much for joining me today. I know it's been a little while, but before the end of the year, much more science, much more gaming, and most importantly, much more hair. No matter where I see your breath, no matter where I see you next time, whether it's on the next live stream, the gaming channel, next channel, fundraiser for little puppies freezing their cute little butts off in Chernobyl, we will help them. No matter where I see you next time, I hope you have a wonderful rest of your day, night, evening, midsummer, and be nice to each other, because this is all we got.